Welcome to the second lecture for week 1. So today we're going to talk about filling rules, and we're going to talk about some more periodic trends. So hopefully you remember from your Gen Chem some of the electron filling rules when we're looking at filling orbitals. So we have Coulombic repulsion, so this is given the symbol large pi sub c or J A comma B. So you'll notice in inorganic chemistry you really have to be careful with all your term symbols because they do get mixed up a fair bit. So this is a destabilization resulting from paired electrons, electrostatic repulsion. So it's derived from the same quantum mechanics as shielding. So if it's a destabilization, that means that it's increasing in energy. The second one is called exchange energy. This is given pi sub e as the symbol, and this is the stabilization due to electron exchange. The quantum effect is written with units of K. So if it's stabilization, again, that's a decrease in energy. So let's ask ourselves a question. Why does nitrogen have a half-filled subshell? So this is something you should probably remember from Gen Chem. But today we'll actually think about why that is and use some quantum chemical arguments to make that argument. So if you look at your periodic table, nitrogen is 1s2, 2s2, 2p3. So if we draw out our configurations for 2s, we have 2 electrons, 2p, remember we have 3 orbitals, and you would probably draw it like this because you remember that you should always fill the electrons unpaired first. But why can't we have some other options? Why can't we do this? And why can't we do this? So you would have probably said that you want to have a half-filled subshell where all the electrons are unpaired. And you're correct. These are excited states. And the first one is the ground state. But the real reason is because of exchange energy. So if we look at some examples, if we look at our p orbitals, if we just have one electron, we have no exchange. So remember, K is the units. So there's only one electron. It cannot exchange spots with another one. If we have 2 electrons, they can change spots once. So they can have 1K of exchange energy. And if we have 3 electrons, then they have 3K of exchange energy. So it's not quite so simple as just counting electrons. There's actually a formula. So for 1, 2, and 3, those you can pretty much learn and memorize. It's useful. But the actual formula that you will have to memorize, so star it up, is that pi exchange is the sum of the number of alpha spin electrons times alpha spin minus 1 over 2 plus the beta times beta minus 1 over 2. So where n alpha equals the number of spin up electrons and n beta equals the number of spin down electrons. So if we look at, for example, 6 electrons in our 2p orbital, our spin up we have 3, so 3 times 3 minus 1 over 2 plus 3 spin down times 3 minus 1 divided by 2 equals 6. So we have 6K of exchange energy in this case. Really important to note, you cannot exchange spin up with spin down because it takes energy to flip the spin of an electron. So if we go back to our nitrogen example, we draw out our possible configurations. The pi exchange for the 2p's. In the top case we have 3K. In the next one we have 1K. And in the last one we also have 1K. And the reason for that is that this one is spin down. The one other thing is that in this case we actually also have repulsion. So remember, pi c is our repulsion. In the first one there are no paired electrons, so we have 0. The second one we have 1, so we have minus pi c. And the last one we also have 0. So this now again tells us that the top one is the most stabilized, so 3K. And remember, stabilized means lower energy. And so that is why that's our ground state. So we'll do another example. We're going to now look at the D block elements. So we're going to compare scandium, titanium, vanadium, and chromium. So once I finish writing out the question, I recommend that you pause and try to do this on your own using the arguments of exchange and repulsion. Okay, so chromium is where this trend starts to fall apart. So chromium is actually best described as 4s1, 3d, 5. So your question is why? Why not 4s2, 3d, 4? So if we draw out these configurations, our 3D orbitals, remember they have 5 orbitals, so 1, 2, 3, and 4, 5 electrons in this case. Our 4s has 1 electron. So in this case, let's count up. There is no repulsion, but we do have exchange. So this one, 4s, has no exchange either. So the 3D does have exchange. So if we look at our exchange formula, we have 5 spin up electrons, so 5 times 5 minus 1 over 2. We have no spin down. And so total we have 10K of exchange. If we now look at our second option, we have 4 electrons in the 3D, 2 in the 4s. So now we do actually have repulsion in our 4s, so we have minus pi c. But again, the 4s doesn't have exchange, so 3D has exchange. So here we have 4 spin-up electrons times 4 minus 1 over 2 plus 0. So you should have 6K. So our total stabilization for the first case is 10K, and for the second case is 6K minus pi c. So in this case, this is more stable. So lower energy. Okay, so now we'll continue and look at some more periodic trends. So if we look at ionization energy, this is given the abbreviation IE. So this refers to the energy needed to remove an electron from an atom in the gas phase. This is really key. A lot of our quantum chemical expressions refer to the gas phase, so when we do use them for a laboratory experiment in the solid or solution states, we have to be careful. So the formula or the equation that this then describes is going from a gas, turning it into a cation, and removing an electron. The trend that you hopefully have seen before is that it increases across a period and decreases down the group. So here's a plot of the ionization energy. So the first thing I'd like to point out is notice if we look compared nitrogen and oxygen. So generally it is following the trend, but oxygen is actually lower ionization energy than nitrogen. So the question is why? So why is the ionization energy for nitrogen higher than oxygen? So again, try to rationalize this yourself using the repulsion and the exchange trends we talked about. So if we draw the 3p configuration for the 2, for nitrogen we have 3 electrons, and for oxygen we've now added 1 additional electron. So if we calculate our exchange, in both cases we have 3K of exchange from all of our spin-up electrons, but in oxygen we now have repulsion. So nitrogen doesn't have any repulsion, and in oxygen we'll have minus pi c. So our total stabilization will be 3K for nitrogen and 3K minus pi c for oxygen, which means that this is less stable. So if it's less stable, it means it's higher energy, and it means it's easier to remove an electron, because removing an electron will make it lower energy. A couple other comments on the plot is that for transition metals, so this is the D block, and this is what a lot of inorganic chemists study. So the inorganic community does study pretty much the whole periodic table, but the D block has a lot of research going on. So for the transition metals, the ionization energy trends tend to level off. And so there are two reasons for this. So the D electrons, if you remember from the first lecture, are relatively poor at screening. And we also have competing effects of s orbital contraction and d orbital expansion. So we're going to look at some of the ionization trends if we look across the transition row period. So we're going to compare ruthenium, rhodium, palladium, and silver. So again, if you're not familiar with symbols for the periodic table, definitely spend a little bit of time familiarizing yourselves. So if we look at our ionization energy in electron volts, for ruthenium it's 7.36, then we go to 7.46, 8.33, but then for silver we go back down. In this case we can write out what the ground states are. So 5s1, 47, 5s1, 48, 5s0, 4d10. So we could think of it as silver being lower, or we can think of it as a spike for palladium. So why does ionization energy spike for palladium? And so we want to compare rhodium versus palladium. And so we're going to look at rhodium by itself. So rhodium by itself we wrote is 4d8 and 5s1. If we compare it to rhodium plus, which is what would result from ionization, we would end up with 5s0, 48. So now we would just have and so in this case, if we calculate our exchange, we have 5 spin-up electrons, so 5 times 5 minus 1 over 2, plus 3 spin-down electrons, so 3 times 3 minus 1 divided by 2, so it'll equal 13K. And it'll be the same for this one. For palladium, if we look at our 4D configuration, we have 4D10. So our exchange will be 5 times 5 minus 1 divided by 2 plus 5 times 5 minus 1 divided by 2, which will equal 20K of exchange. For our ionization, we now will have 4D9. So our exchange energy will be 5 times 5 minus 1 over 2 plus 4 times 4 minus 1 over 2, which will be 16K. And so in this case, this is a difference of 4K of stabilization. And so it takes a lot more energy to overcome. The next trend we'll look at is electron affinity. So this you probably see as EA, not to be confused with activation energy. So you were probably taught that this is the gas phase element, and you add an electron to it to make the negatively charged species in the gas phase. This is generally exothermic. Remember, it gives off energy. Again, in the gas phase. We actually write it the other way. So this is important to remember. We actually write it as the element in the gas phase, anion, going to the neutral plus an electron. So you can see the way it's written out is actually quite similar to how ionization energy looks, except that you're starting with a minus charge. And so this is now generally endothermic. And so if we look at some examples, carbon minus going to carbon plus an electron, our electron affinity energy is 119 kilojoules per mole. And for nitrogen minus, it is 4.6 kilojoules per mole. So this is a pretty big difference for just going from one electron difference in an element. So the key is, if we're looking at carbon minus, we have 2s2, 2p3, going to carbon, 2s2, 2p2. Whereas if we go from nitrogen minus, we have 2s2, 2p4, going to nitrogen neutral, 2s2, 2p3. So in nitrogen, well, let's start with carbon. So in our P's, we have 3K of exchange here. We have 1K of exchange here. In nitrogen, we have 3K of exchange in both. But for nitrogen minus, we also have a repulsion. So in this case, in nitrogen, we are decreasing repulsion, and so it is a net stabilization. And so that's why that takes so little energy to overcome. So the first electron affinity is generally endothermic. The second is always endothermic. So if we look at our chart again, here on the bottom we have our electron affinity trend. Okay, so next we're going to look at atomic radii. So these generally increase down the group and decrease across the period. Couple things to think about. It depends on how you measure the radii. So we could have covalent radii, we could have ionic, or we could have van der Waals. And the last trend we're going to look at is electronegativity. This is often given En. It's also written as chi. Electronegativity is the most confusing one, so there are many definitions. And so I really just want to give you an idea of what the concept is and kind of show you that it's something that's very useful as a trend when we're looking at making molecules and studying new systems, but you have to be a little bit careful if you're trying to quantify it. So Pauling came up with the definition that it's the power of an atom in a molecule. So notice this is totally different from all the other periodic trends where they're all just a single atom in the gas phase, to attract electrons to itself. This was a generalization with very limited data. He set fluorine to 4.0. He observed that polar covalent bonds are typically stronger than nonpolar bonds. There are several other electronegativity scales. You should just be aware that they exist. So if you do end up looking more into electronegativity, that you're careful. The one thing about all electronegativity scales, transition metals have a really small range of electronegativities. And so generally, it's not a good indicator of reactivity for transition metals. What you can use the electronegativity scales to look at is to try and look at bonds. So if we have ionic, that would be a complete electron transfer. Covalent would be shared electrons. Localized and directional. And metallic is shared electrons, delocalized, and non-directional. So that's it for the periodic trends section. The next section will be about anomalies.